So a bit of a review on some of the topics that we've covered in the past couple of weeks. You may remember when we studied viscosity, we saw that Newton's law of viscosity related the shear stress acting on a fluid to its velocity gradient or velocity profile. So we saw that Newton's law of viscosity said that shear stress was equal to some constant, which we call dynamic viscosity, times du over dy, where du is over dy is what we call the velocity gradient or the strain rate, which is the change in velocity with respect to depth. Now this is all good, but let's remember that this was considering what's essentially a one-dimensional flow, right? If you look at a one-dimensional flow, you have your x-axis and your y-axis, but then your flow really only travels along the x direction, then you can definitely quantify that du over dy as your velocity gradient. And then the shear stress that results from this one-dimensional flow is right here or right here. Now, from the context of the stress tensor, which if you don't recall the stress tensor, it's essentially a tensor that shows that every stress acting on a fluid particle can be divided into three components: two tangential or shear components and one normal component. So from the context of the stress tensor, we may have recalled that the stress tensor related the stresses based on the face of the face in which the stress is acting on and the direction in which the stress is acting on. So for a fluid particle, a three-dimensional fluid particle, we know that in each face, for each face, we can identify three stresses: one normal stress and two shear or tangential stresses. And if we're looking at this in Cartesian coordinates, where this is my x-axis, this is my y-axis, and this is my z-axis, then we identify each member in the shear stress tensor based on the face in which it's acting on and the direction. So for example, this is a normal stress, so I'm going to call it sigma. Normal because it's orthogonal or perpendicular to this face. And notice that this sigma, this stress, is actually acting on my x face. Why is this my x face? Because the area vector for this face, which is always normal to the face, points in the x direction. So if you look at a normal vector to this face, it's pointing in the x direction. So the sigma that acts on the x face, and in which direction is this vector acting on if it's also normal to the face? In the x face, right? In the x direction. So this is sigma xx because it's the normal stress that acts on the x face in the x direction. And then we could identify a tangential stress. Let's look at this one, for example, as tau. We know it's acting on the x face, so it's tau x. But in which direction is this vector acting on? The y direction, right? So this is tau xy. Likewise, this will be tau xz, sigma yy, sigma yx, sigma tau yx, tau yz, and so on. So based on that information, I think we can understand that this equation of Newton's law of viscosity for one-dimensional flow really is only giving us one of these stresses, because we're only looking at the stress, in this case, the stress that's acting on the y face, right? This will be my y face because the vector, area vector for this face is normal to the face, so points in the y direction. In the x direction, that's correct, thank you. So this is actually tau yx. Now, if this is tau yx, and we know that the shear stress is related to the viscosity of the fluid and some movement property of the fluid, so the velocity gradient, then how do we find the stresses in the other faces? Well, the answer is just like Newton found this law, it's empirically, right? We mentioned that viscosity was an empirical measurement. We didn't derive it analytically. Instead, we had to take various measurements in order to say, okay, for this particular fluid, this is the proportion or the rate of the constant of proportionality at which the velocity gradient is related to the shear stress. And if we repeat these experiments for multiple types of fluids in multiple directions for three-dimensional flows, we are going to land at a series of relationships that give you the relationship, I guess, a series of equations that give you the relationship between shear stress acting on each face of a fluid to its viscosity and its velocity gradient. Now, these equations are combined are known as the constitutive equations. So these are the equations that govern the flow of a fluid based on its viscosity. In other words, they relate the shear stress to the velocity gradients of said fluids. Now, constitutive equations, because they're empirical measurements, they will actually vary between different types of fluids. So instead of giving you every single constitutive equation for every single type of fluid, let's try to focus this lecture on fluids that are going to be commonly studied in this class. So particularly, we're going to study constitutive equations for incompressible and Newtonian fluids. Incompressible, they do not expand or contract from pressure changes, so density can pretty much be treated as a constant if there's no temperature change either. And Newtonian means that the viscosity value is a constant. So that means viscosity will be a constant. It doesn't change with shear stress. Now, these constitutive equations are essentially giving us our stress tensor.
That last part?
Yeah, Newtonian.
Just that line.
So incompressible means that they don't expand or contract with pressure, so density can be treated as a constant. Newtonian means that this viscosity value is a constant. Non-Newtonian fluids don't have constant viscosities. It changes with respect to shear stress.
Does that mean that it wouldn't be a curve there, but a straight line?
Well, this is just du over dy. That's all it is. This is not shear stress. But like you said, if you were to plot shear stress, so we were to plot something like tau y, then yeah, or tau u, then yeah, it would be a straight line. Okay. So one of the things I think we want to understand is that because these are empirical equations, that doesn't mean that you have to memorize them, take them as they are. They still have some patterns to them, and we will be able to identify these patterns. However, because they're not analytical equations, then we can't really try to come up with an expression for them mathematically from some fundamental law. So we can't say, for example, oh, Newton's second law says this, therefore we can get this equation, because there is no relationship like that. They're empirical, so they are from measurements. But you'll see the pattern as we start writing them. So these constitutive equations tell us that the normal stress acting in the x phase in the x direction for a fluid is equal to the pressure acting into that fluid particle plus the viscous pressure term, so the viscous normal term acting towards that fluid particle. So this would be the normal stress, okay? Similarly, the normal stress in the y direction would be equal to the pressure towards the y direction. Remember that pressure at a point is equal in every direction, so we don't really need px or py, it's just pressure, right? Plus the viscous component of that normal stress. And hopefully we are starting to see a pattern here, so that when we get to our normal stress in the z direction, what do you think the normal stress in the z direction will look like?
Negative pressure plus 2 viscosity change in W over change in Z.
That's correct. That is absolutely right? So you can see the pattern here. You can see that the normal stress for these incompressible Newtonian fluids can be quantified by the pressure acting on the fluid, as well as the viscous term and the change in velocity with respect to its own length scale. In other words, the change of the x component of velocity with respect to x, the change of the y component of velocity with respect to y, the change of the z component velocity with respect to z. So these changes actually represent any deformation on the linear or longitudinal scale. But now when it comes to shear stresses, of course, we're looking at shear stresses. So we're not really going to look at linear deformations. We're going to have to look at deformations that are tangential to the fluid particle. So we know, we mentioned last time on last class that for incompressible fluids, the stress tensor tells us that tau ij equals tau ji. So tau xy will equal tau yz. And the constitutive equations show us that, or tau yx. Why did I write z? There we go. And the constitutive equations show us that. So in the case of shear stress in the xy direction, we're going to have a viscous term, no pressure term, because pressure is always normal to the fluid particle, but we will have a viscous term. And then we will have this tangential velocity gradient. Okay? In the case of tau yz, which is also equal to tau zy, we're going to have the viscous term and then the tangential velocity gradient. And then in the case of tau xz, which we know is also equal to tau zx, if you start to note the pattern, what do you think that shear stress will look like?
Tau zx.
Mm-hmm.
Sorry. Viscosity, parentheses, and then partial w, partial z plus partial u partial x.
Close. Notice that we're taking the x component and deriving it with respect to its y distance. So actually it will be partial w with respect to x, partial u with respect to z. Because this actually gives me the shear component, right? The shear deformation. And you can see that now, if this were a one-dimensional flow, then we know that tau yx.
Change in velocity in the z direction. Change velocity in the z direction. For change in x.
Exactly, with respect to the x length. Yeah, that's correct. So we can see here that if we're looking at a one-dimensional flow, then tau yx equals viscosity, dou u, dou y, dou v, dou x. But if the flow is one-dimensional, that means that there is no y component of velocity. This goes to 0, and this actually just gives me Newton's law of viscosity. So essentially,
it seems like it would be acting like diagonal to the edge.
What do you mean diagonal to the edge?
Or like normal to the edge. I mean, thinking about it, like z, so like change in x, like going like this way, and then change the velocity in z, and then change in x like that, and then change in velocity in x, or change in z, like it would go like that, like up. Right?
Well, the net deformation essentially is this.
Oh, okay, yeah, okay. Yeah.
Right, because you have one deformation in this way and one deformation this way, and the net deformation. Exactly. Okay. Yeah. I think this will make a little bit more sense when you take your strength and materials class, because in strength and materials, you actually do these shear diagrams. And then when you study shear acting on a solid particle, and it's a little bit easier seeing it on a solid particle. But exactly, that is correct. Okay. Now, why am I giving you these constitutive equations? Because we're going to use these constitutive equations in order to derive probably some of the most important equations in fluid mechanics, called the Navier-Stokes Equations. And without trying to go into a bit of a history lecture, I think yesterday, like I said, I spent like 20 minutes talking about fluids history. So I'm going to try to be brief this time. The reason these equations are important is because for hundreds of years, right, the study of fluid mechanics was pretty much divided into two separate, and I really mean separate fields, the field of hydraulics and the field of hydrodynamics. people that worked in hydraulics were what we would call now engineers. People that worked in hydrodynamics are the modern day mathematicians and scientists and physicists, right? The reason these fields were kept very separate was because mathematical theory could not accurately model or predict fluid flow. And then practical applications in fluids, right, wouldn't really find any reason to be modeled mathematically because the mathematical models cannot really help these practical applications. So the engineers started building structures, right? Structures relate to fluids, drainage structures, navigation structures, canal locks, etc. Whereas the mathematicians started dealing with equations, trying to understand from the physics side, from the equation side, from the math side, how fluids work. But there was always a bit of an irreconcilable difference between the results of experiments from the engineers and the results of theory from the mathematicians. However, when Navier and George Stokes derived a set of equations of motions, they actually derived them independently, but we call them Navier-Stokes because they arrived at the same conclusion more or less near the same time. They actually managed to find a way to include these shear stresses into the motion of a fluid. And with the Navier-Stokes equations, the study of fluids actually came to, I would say, a bit of a breakthrough. A breakthrough because now we can accurately model and predict fluid motion, including its viscous shear stresses, and it actually led to pretty much a combined field of fluid mechanics that included both theory and experiments. So whereas before Navier-Stokes, fluid mechanics was two completely distinct fields that did not work together and did not want to work together because they could not work together, after Navier-Stokes, fluid mechanics became pretty much a very interdisciplinary field that could benefit from both experiments, so engineering, as well as mathematics or physics. So that's why these equations are important. Now, I'm not going to lie to you. You're not going to graduate, go into industry, and suddenly have to write down the Navier-Stokes equations to solve something. However, I will be honest in that whatever equation you do end up using to model some flow in the field is probably derived from Navier-Stokes. So what we're going to learn in this class is how to derive Navier-Stokes and then how to use Navier-Stokes to come up with fluids equations that we can use in everyday life.
I was just looking at the shear stresses. So is the tau xy, that's the one on the left face pointing to the right, isn't it?
So
the first value is the phase, the second value is the direction.
Exactly. So this one will be in this face pointing towards this direction.
Tau yx would be on the right face pointing to the left, right?
So this one.
Yeah, that's tau yx.
Yep.
So why are those equal? Because they're not pointing in the direction.
They're acting like that, and you have to have what's the
Wait, can you let him enter?
Yeah, that's exactly the same, right? So they're both acting in this direction, so they need to be equivalent, right? If they're not equivalent, then my fluid has to change its density, right? The volume of the fluid has to change. And that's why I mentioned it's a little bit easier when you take strength of materials class because those professors actually explain it better than I do. But if you're, whatever shear stress you apply in this direction, right, in this direction, you have to apply an equivalent shear stress in this direction. You have to. Okay. If you don't, then you're going to have relative deformation that essentially changes your volume. And then it wouldn't be an incompressible fluid. Okay? Yeah, it's not my area of expertise, to be honest. So that's why I feel that strength professors do a better job of explaining this than I do. But essentially, we have our constitutive equations, and now we're going to derive the Navier-Stokes equations for incompressible Newtonian fluids. There is a movie. It's not real. It's fiction, right? But it's with Chris Evans, and it's about this genius girl who is this math prodigy, and one of the centers of the movie, right, was the whole thing about solving the Navier-Stokes equations problem. It has nothing to do with fluids, but the fact that they include that actually makes the movie quite interesting for people that, that study this. So you may want to watch it. It's called Gifted. So how do these Navier-Stokes equations work? Well, in order to derive Navier-Stokes equations, we need to start with the Cauchy equations of motion. But then we're going to apply the shear stresses and the normal stresses from these constitutive equations into the Cauchy equations of motion. And then we will land at the Navier-Stokes equation. So let me start first by writing down the equations of motion in the x direction. We're not going to do x, y, and z. We're going to do x, hopefully find a pattern there, and then apply that pattern to y and z. I think that's a better way to study this topic, right? So in the x direction, if you didn't watch the last class video or read the notes, then I'll just give you a quick review. In the x direction, we found through some interesting but long derivation that we can describe the motion of a fluid through the following equation. And my hope is to explain what these terms mean so that we can then see how we can apply the constitutive equations to the terms themselves. So this is the equation of motion for a fluid in the x direction. It's essentially the conservation of momentum equation, but in differential form rather than an integral control volume form. So what do these terms mean? Well, what we're saying here is essentially the mass times acceleration of a fluid particle per unit volume, right? Mass per unit volume is density, and then acceleration you can see as the material derivative of the velocity. And this is actually equal to the sum of forces in a fluid particle. So Newton's second law of motion, right? Sum of forces equals ma. And the sum of forces will include the difference in normal stress along the x direction, the difference in shear stress acting on the x direction along the y direction, the difference in shear stress acting along the x direction along the z direction, okay? And then we have our body forces. When I say body forces, what do you think I mean? Gravity is one of them, right? Exactly, electromagnetic forces. Any force that really is dependent on the mass of your body. Now, because gravity is the most common body force, we're gonna write G to represent our body forces. But let's remember that this G is the acceleration component for all your body forces. It can be just gravity, it can be gravity and electromagnetism, it can be any body force, any force that depends on your mass. Now, in order to start applying the constitutive equations to these equations of motion, let's remember that our velocity vector can be described by three components in the x, y, and z directions. And we can see here that we'll be expressing our body force acceleration vector, which you can treat it as your gravitational vector, as a vector with three components in the x, y, and z directions. So let's keep those things in mind, and hopefully it will allow us to simplify or understand how we are manipulating the terms in this equation. Now, if we were to apply the constitutive equations into this equation of motion, what do you think we need to start changing or doing? So we know we have the mass times acceleration per unit volume. So what will we have here for our first stress term? So we're looking at the change in normal stress xx with respect to x. So first off, what is that normal stress if it's an incompressible Newtonian fluid?
Negative P plus 2 times the viscosity times the partial of U with respect to x.
Exactly, right? We have our normal stress in the x direction. And so we can apply. We have the partial derivative with respect to x of negative P plus 2 viscosity times dou U dou x. So if I write it down, this will be negative partial change in P with respect to x plus, I'm going to take 2 viscosity out of the derivative because they're constant. It's a Newtonian fluid, so mu is constant, so I'll take it out of the derivative. 2 mu change with respect to x of dou U dou x, right? So this is essentially substituting this entire term in this expression, in this operation. In the y-axis, we have the change with respect to y of tau yx. And what would that look like? First off, we know that tau yx is equal to tau xy, so it's actually just this term. And if we see here, this should give me, factoring out viscosity because it's a constant, we'll have viscosity times the change with respect to y of dou u dou y plus viscosity again plus the change times the change with respect to y of dou v dou x. And then if we apply the change in tau zx, we know that tau zx is equal to tau xz, so we have it right here. This will give us factor out viscosity, so viscosity times the change with respect to z of dou w dou x plus viscosity times the change with respect to z of dou u dou z. And finally, we must not forget our body force, so I'll write it down. Like many, if not all of our derivations, it looks like we took what was already a complicated equation and made it even more complicated. But let's do some mathematical manipulation, and we'll see that we will actually be able to simplify this equation by a lot, okay? So manipulating a little bit, let's keep in mind the following. We have 2 viscosity dou x of dou u dou x. And I can actually express that, and I'll just write it down here. We know that 2 mu dou x dou u dou x is actually the same as mu dou x dou u dou x plus itself. Do we agree with this transformation? Right? If you add these two, you just get 2 times the term. And the reason we're doing that is because it's going to allow us to organize our numbers a little bit better. So what does that leave us with? I'm going to try to use as much of the paper as I can. So we got density times acceleration equals negative change in pressure with respect to x plus, and here I would like to keep all of my dou x, dou y, and dou z. I'm going to keep those together, those terms together, okay? So this will give me mu dou x, dou u, dou x, plus, and just so that I can keep track, I'm just going to underline the terms that are already written down. So I have one of these two. I'm going to keep my dou y's together. Mu dou y, dou u, dou y. I'm going to keep my dou z's together. Mu dou z, dou u, dou z. Hopefully you will start to see a pattern here as we start to organize all of these terms. Then I'm going to include all of my other shear stress terms. Okay, so we have that equation. Does it look easier to manage? Actually, no, it looks a little bit harder. But the reason I'm organizing them this way is because now we can see that there's actually some patterns that we can recognize in these terms. And before we start recognizing patterns, let's talk a little bit about math in the physical world. Most physical equations, in order for them to be actually physically plausible, have to be smooth. And what I mean by smooth is that they have to have discernible results and derivatives throughout their entire domain. Now, I think this should make sense, right? If you have a physical equation, then that means that that equation needs to have a solution for all points in physical space. Not all mathematical equations have solutions for all points. For example, you can look at the equation y equals 1 over x. You know that there's no solution for that equation when x equals 0, right? There is no solution. So can we say that that's a physical equation? Not really, right? We're going to have to find other ways to model physical aspects or physical properties that seem to follow that trend. However, because we're dealing with fluids, we should be dealing with a physical equation. So I'm going to start by making the assumption that these equations have discernible solutions and derivatives throughout. And what that means from a mathematical perspective, what that means is that I can say, and I don't want to take too much space off here, so I'm just going to write it up here. If f, which is some physical function, is a function of x and y, yeah? Oh, I didn't see you.
How come down below there's two partial derivatives over dx?
Where?
At the beginning and then right there above the middle.
Because this is 2 times this, so we just split it up into two of those terms.
So why do we separate them?
Well, we separated them just so that we can organize them in this way. That's all it is. It's just mathematical manipulation right now. We're not doing anything to change the equation. We're just moving terms around, okay? So what I'm going to say is that for any function that's physical and that depends on two independent variables, x and y, then the second derivative, so dou x of the function with respect to y, should be equal to dou y of the function with respect to x. So that is the assumption I'm going to make. And this assumption has to be true if these equations are going to be physical equations. If not, then these would not be met. So what this means is that if you take the second derivative of the function with respect to two of its variables, it doesn't matter in which order you take the derivative, your second derivative should still be the same. So if you derive f with respect to y, and then derive that with respect to x, that should be the same as if you derived f with respect to x, and then derive that with respect to y. It should be the same. Sorry?
Is that if the function never equals 0?
That is for any physical function. For any function that's physical. Okay? There's a topic called the smoothness, right? A mathematical smoothness, but we really don't have time to cover it here. But essentially, if our equations are smooth, then this is one of the conditions that needs to be met. Okay? So why am I doing this? Why do I say this? Well, the reason I'm saying this is because notice that we have second order derivatives here with respect to different variables. And if these equations are indeed physical, then this needs to be true. And if this is true, then that means that I will be able to flip these terms. Because even if I flip them, the answer should still be the same, right? The derivative of v with respect to x, and then take that derivative with respect to y, should be the same as even if I flip the terms in which I derive. Okay, that's what we mean when we say a physical equation. And why do I want to do that? Because now we can start to identify these somewhat obvious patterns. Notice one thing. I have my density and my acceleration. I know that I have my pressure gradient in the x direction. Okay, what do these three terms have in common? Okay, we have a viscosity term. And notice that in addition to the viscosity term, we're looking at the second derivative of u with respect to x, right? Because we derive u with respect to x, and then we derive it again with respect to x. That's just the second derivative, right? So we have the second derivative of u with respect to x. What do we have here? Exactly, a second derivative of u with respect to y, and the second derivative of u with respect to z. And that's starting to look a little bit cleaner. We haven't seen this term before, but does that term remind you of something? Perhaps not specifically second derivatives, but notice that we are looking at change with respect to x, change with respect to y, change with respect to z. Does that remind you of something? The what? Not quite. The gradient, right? The gradient. And we'll see that this term is actually related to that gradient. And we're going to see how in just a second. So let's go to these three terms. What do these three terms have in common? Exactly. We have a viscosity term as well as dou x. Because if I flip these terms, I will essentially apply this dou x operator to them. And then inside, I'm left with dou u dou x plus dou v dou y plus dou w dou z. And finally, my body force term. Has anybody seen this before somewhere? The divergence, right? The divergence of the velocity. Remember that del dot v is actually equal to dou u dou x plus dou v dou y plus dou w dou z. So we actually have the divergence of the velocity field, and it's actually right here in front of us. Okay? So that's one way we can start simplifying, right, this problem. And the reason, right, I want to simplify this problem is because we'll see that these little terms that kind of seem to be related to my divergence can actually be written or expressed in terms of this del operator. I have a question, and this is just a bit of a mathematical exercise here for us. We know that del dot v, we operate it like a dot product. So we have dou x times the x component of v, plus dou y times the y component of v, plus dou z times the z component of v. But what if we were to take del and dot it against itself? What would that give us? Can you say it again? The second derivative with respect to what? Well, what is the del operator? Del operator is derivative with respect to xi plus derivative with respect to y j plus derivative with respect to zk. So what does this give us? Del dot del. Exactly. This operator is called a Laplacian. Does anybody know who it was named after? Laplace. All right. And now, where do we see the Laplacian here? We see it right here, right? We see that this is actually the Laplacian applied to the x component of the velocity field. And that's essentially what it is, Laplacian applied to the x component of our velocity field. No, it's just an operator. It's like applying the gradient operator, but here we're applying the Laplacian operator. So it is an operator, yep.
Don't people also say like Laplacian when they're taking the Laplace transform?
Yep.
So it's the same word, has two different meanings?
No, it's actually the same thing.
It's the same thing?
Yeah, if you do a Laplace transform, you end up with the same thing, right? Change with respect to the three coordinate systems.
Oh, really?
Yeah. Yes, that's the good thing about math, right? Everything kind of like comes together somehow. It may look different. We may be using different signs and different terms, but it's actually the same thing. I think you're the only person that actually made the connection. So that's pretty good. That is good. That is pretty good. Good. So what does this leave us with? This leaves us, and I'm going to have to take my initial sheet out of the way, but this essentially leaves us in the x direction with a pretty understandable equation. We get that the density times the acceleration, and this is all x component. Remember, this is all for the x direction of my velocity, is equal to negative dou p dou x plus mu Laplacian of u plus mu dou x of the dilatation rate, or the divergence of the velocity field. And don't forget your body force. I'm going to keep repeating that body force term because one of the things, we focus so much on stresses and pressures that we sometimes tend to ignore or forget our body forces. So let's not forget our body force. If we were to do the same derivation in the y direction, how do you think it would look like? Without having to derive it again. But if we were to derive it again, right, what do you think the equation would look like?
V dt equals negative partial p partial y plus mu Laplacian, v plus mu partial over partial y, then it would be the divergence or partial. What's it called again?
The dilatation rate or the divergence of the velocity.
Plus density and then the material the gravity.
Yep, that's correct. And then of course we know that if we were to repeat the process yet again in the z direction, we'd get density times the acceleration in the z direction equals negative change in pressure over the z direction plus viscosity Laplacian of the z component of the velocity plus viscosity, the partial change with respect to z of the dilatation rate plus density times the z component of acceleration. And why does that matter? Because now we can take these three equations and express it, I would say beautifully, into one vector equation. Remember, a vector f is the sum of its x, y, and z components acting in the x, y, and z directions. So we can actually take these three components, add them up in their x, y, and z directions respectively, and land at a vector form. Now, what would that look like for us? And I'm going to try to take advantage of the fact that I already have these three equations written down nicely. If I were to add rho du dt I plus rho dv dt j plus rho dw dt k, what do these three terms have in common? Is there anything that I can start to factor out? Rho. And what else?
ddt.
Exactly, the material derivative. So I get rho ddt of ui plus vj plus wk. Has anybody seen this vector before?
Velocity, isn't it?
Yep, this is just my velocity vector. If I add these three terms, negative dou p dou x minus minus dou p dou y minus dou p dou z, what do these three terms have in common? Well, I guess there's a -1 there, right, that we can factor out. Okay, so we factor a -1. And we get dou p dou x plus dou p dou y plus dou p dou z. Where have we seen this before? In the x, y, and z directions. Maybe if I write it down, it'll be a little bit easier. Dou p dou x I plus dou p dou y j plus dou p dou z k. So where have we seen this before? Close, close. It's an operator. The what? Not the divergence, right? Divergence is del dot something, and that's a scalar. But what operator gives us a vector? The del operator, right? Notice that this is actually just the gradient of the pressure, or the pressure gradient, okay? If I add mu Laplacian u plus in the x direction, that's I, plus mu Laplacian vj plus mu Laplacian wk, what do these three terms have in common?
Mu Laplacian.
Okay. And we already know that this is just our velocity vector. I'm going to have to, I think I have space. If I add mu dou dou x of something I plus dou dou y of something j plus dou dou y of something k, and here, remember that this divergence is a scalar, that's one thing. And two, for all these three terms, the divergence is exactly the same. So instead of looking at this as the divergence of something, maybe think of it as a scalar, right? So we have dou of a scalar dou x, dou of a scalar dou y in the y direction, dou of a scalar dou z in the z direction. What is that again? The gradient, right? So what do we have in common here? We have our viscosity term in common. And then we have dou x of something I plus dou y of something j plus dou z of something k. That is just the gradient. And what is that something? The divergence of the velocity field. So this is actually just the gradient of the divergence of the velocity field. And of course, let's not forget our body force, which should be relatively simple, right? We can factor out our density. Then we get gxi plus gyj plus gzk. And we know that this is simply our body force vector, body force acceleration vector. And finally, this leaves us with a beautiful set of equations known as the Navier-Stokes Equations, where we get that the density times the acceleration, that's the material derivative of the velocity field, is equal to negative the gradient of the pressure field plus viscosity times the Laplacian of the velocity field plus viscosity times the gradient of the dilatation rate plus my body forces. However, remember, we are using the constitutive equations for incompressible Newtonian fluids. So for incompressible Newtonian fluids, what else should I do to this equation? Keyword, incompressible. Okay, density is constant, but that really just tells me I can, divide by density or something. But what else? There's something key here. So let's remember conservation of mass. This is the second form. If my fluid is incompressible, what does this term become for an incompressible fluid? If my fluid is incompressible, density is a constant. Can I factor it out? Eliminate it? So if my fluid is incompressible, we know that the dilatation rate has to be 0. So what can we do for this equation?
Take out the part.
Exactly. Del dot V equals 0. The gradient of 0 is 0. Mu times 0 is 0. So we can get rid of this term. And now, I spoke too soon earlier. Now we arrive at the equation that essentially describes fluid motion for incompressible Newtonian fluids. These are the Navier-Stokes equations. Equations, plural, because we have 3 equations that can be formed from these vectors. Beautiful. Why are they beautiful? Well, just look at it. Such a clean equation with very discernible terms. You can really factor out the pressure, the viscous term, the body force term. It's all very organized. It's all very nice. And it is the basis for deriving expressions for fluid flow. Now, for some situations, finding solutions to the Navier-Stokes equations, which we typically use to find the velocity field. Finding these velocity fields is easy for some situations. We can find exact solutions. But for most cases, solving the Navier-Stokes equations becomes really hard. And let me see if we can figure out why. So for the Navier-Stokes equations, we typically use it to find V, right? Find the velocity. given some of these three terms. So given the pressures and the stresses, so given the stress tensor and the body forces. Why do you think finding velocity can be hard sometimes in this equation? First off, mathematically, what type of equation is this? We have derivative of velocity with respect to time, second derivative of velocity with respect to space. What type of equation is this? An equation that deals with derivatives.
It's a partial differential equation.
It's a partial differential equation. But beyond that, in addition to being a partial differential equation, what's the order of this partial differential equation? Second order, right? And beyond that, not only do we have a second order derivative here, but the first order derivative isn't even with respect to the same variables as the second order derivative. What we have here is a very hard equation to solve, well, for some cases, right? For most cases. However, we know that it describes fluids perfectly because when we try to solve it numerically, when we try to solve it empirically, we find that the equation actually does model fluids pretty accurately. Solving it theoretically may be hard, may be really complicated, but it's not impossible. And today, with our last 20 minutes that we have left, we're going to use the Navier-Stokes equations to come up with a simple fluid equation, velocity equation, that you will see in your work. Okay? And like I said, the purpose of this class is not for me to give you equations that you're going to use forever. It's to give you the tools so that you can find those equations and not have to memorize them. And that's what we'll do today. We're going to start with Navier-Stokes, and we're going to use it to solve for the velocity field of a specific type of flow. But before I do that, are there any questions? No? All right. So let's start. Navier-Stokes equations, remember it. Pretty important set of equations in fluid mechanics. And now, let's use the Navier-Stokes equations to derive an equation for the velocity field of a fluid. And
Technically use it on a non-Newtonian fluid.
With different constitutive equations.
Like it wouldn't go down to that one that we just found, but
It'd be a little different.
if you took like the original way we started solving and we solved it, if you kept a couple things from there, if they
Yep. If you're looking for non-Newtonian or compressible fluids, you would start with different constitutive equations, then plug them into the Cauchy equations of motion, and then you will land at slightly different equations. They're actually not that different.
It look like that, but longer.
A little bit longer. Yep.
You're just using the formula that you have to bring into this one for a non-Newtonian.
You can't just use the formula that we have for non-Newtonian, right? It just for Newtonian and incompressible. Yeah. Yeah. And the reason we're doing Newtonian and incompressible is because really we are undergraduates, right? So let's not complicate ourselves too much. But you can actually use it, and once you have the right constitutive equations, you can apply them into the equation of motion and derive very similar looking equations with an additional term here and there. Okay, that's going to account for the compressibility or the viscous term. Okay, so let's look at an example. I'm going to give you a very, very idealized flow situation. And the reason we're idealizing this flow scenario so much is so that we can actually find an exact solution for the Navier-Stokes equation. Okay, so we're going to find an exact solution for Navier-Stokes for a particular flow. Now, this is actually not in your notes for this week, but it will be in the notes that I post for next week. Okay, so don't be worried if you don't see it in your notes this time. Let's say that we have flow traveling through what's called a channel. And here I want to make a bit of an observation I made this semester. Us civil engineers, we define channels as these boundaries that bound the flow on its bottom and sides, typically open to the atmosphere. Exactly. However, mechanical engineers, they define a channel as any boundary that bounds the flow, leaving some free dimension But that free dimension normally is not open to the atmosphere. It's simply an infinite dimension, an infinite domain. Like what?
Like the ocean would be a.
Well,
Yeah, you're supposed to
we can call that a channel, but for mechanical, we civils.
You said coming from some sort of
Infinite domain. So, and what I mean is, for example, when you're looking at something like the flow of lubricating oil in a gasoline engine, right? We have very, very thin stretch of fluid, right, of oil in between the piston and the whatever cylinder, right? Now, when we study that, because it's so thin, we can actually take the dimension, the radial dimension, the angular dimension, as if it were an infinite domain. Because it looks like the only viscous effects are coming from the top and the bottom, from the container and the piston. So there are no viscous effects coming from the sides. The only effects are coming from the top and bottom. So we treat it as if it were an infinite domain angularly. And that is what mechanical engineers, at least from my experience this semester, where I've had more of an interaction with mechanical engineering, it seems like that's what they call channel. Something that is bounded by some dimension, but infinite in the other dimensions. Whereas for us in civil, we call channel something that is bounded by 3 sides and then open to the atmosphere on one side. And I want to make that clear because I'm going to call this a channel, but it's not like an open channel. It's not like a river or something. It's simply what I'm saying, fluid travels bounded in the top and the bottom, but not bounded on the sides. What that means is that we're looking at a channel, fluid traveling through 2 infinitely long plates, very, very infinitely long plates. Plates where there is no viscous effects from the walls at the end, right? They're infinitely long, so the ends should be at infinity, so the viscosity from the ends do not really affect. Any questions? All right. So we have fluid. Our fluid is traveling in this direction. We have a couple of dimensions, right, given for this channel. Let's say that this channel has a width of A. That means that fluid can travel freely in this range of width A. And the reason I'm drawing it a little bit inclined is so that I can say that the channel is at an angle theta from the vertical. And what does that mean? That means that my gravitational force, which we call weight, acts vertically downward. But the channel is not in line with that gravitational force. And that's just so that we can get, we can start to apply gravitational fields even in the x direction, okay? As far as my coordinate systems go, I'm going to call this my x direction. I'm going to call this my y direction. And I'm going to say that normal to the paper, that is pointing towards u, we have the z dimension, okay? This channel, right, fluid is flowing. In order for fluid to flow, there has to be either a pressure or a shear stress or a body force, right? We get that from Navier-Stokes, right? In order for fluid to flow, in order for there to be some acceleration in the fluid, there needs to be a pressure, a shear stress, or a body force. So if this is my fluid right now, ignore this flow line. If this is my fluid right now and I have my gravitational force acting on it, in which direction is the fluid flowing? Yeah, right? The fluid, if gravity is the only thing acting on the fluid, it should be flowing in this direction. But if we want it to flow in that direction, we're going to have to apply a pressure gradient. In other words, we're going to have to exert some pressure at one end of the fluid, and the pressure essentially reduces itself as the fluid moves on. That's what we call a pressure gradient. For pressurized systems, systems that are not open to the atmosphere, fluid always travels from the point of highest pressure to the point of lowest pressure. That's something that we should know. And even if we didn't, we can see it here with the Navier-Stokes equations because we have negative P. That means negative gradient P. That means that if our pressure has a negative gradient, so if our pressure decreases in one direction, right, negative, that means that flow is moving in that direction. That's what this negative term means. Okay, if my pressure decreases in one direction, flow moves in that direction, which means that flow always travels from the point of highest pressure to the point of lowest pressure. Okay, so we apply a pressure field, and let's say that this pressure field, just for the sake of it, let's say that we're applying a pressure field and that there's no gravitational force. If I ask you to draw the shape of the velocity profile of this fluid, what do you think that profile would look like? Do you think the velocity is the same at every point? What do you think? No, why not? There's friction, right? So what would that velocity profile look like if I ask you to draw it? Like a parabola or a circle, right? So something like this, where the highest velocity is at the center, and then there's zero velocity at the sides. Does everybody agree with that? Good. Let's say there is no pressure, no gravitational force, but rather the top plate moves with a velocity of capital U. So no pressure, no gravitational force, but my top plate is moving. What would that velocity profile look like? Yeah, something like this, right? Where you have the highest velocity here, and then zero velocity here, right? Okay. So if I ask you to come up with equations for these three motions, I think you have a pretty good idea of what the velocity profile looks like, right? First of all, we can see that for each of these three motions, fluid always moves in the x direction, and the velocity really only changes with respect to y. It doesn't change with respect to x. If you look at 2 points at the same height in this channel, at 2 points at the same height in the channel, they should have the same velocity. However, if you look at 2 points at different heights in the channel, they're going to have different velocities. So I want to make sure that we understand that. And now let's combine all three: gravitational force, pressure force, and the movement of this plate. What would that velocity profile look like if you combine all three forces?
It's going to look like that with more of a, like almost a,
So something like
a slightly smaller and like that.
All right, I don't know. I think it's going to look like something like it's trying to make an S, but not really, but failing at it. Who knows? But it's okay, because we're going to find out the equation that describes that velocity profile exactly. And then all you have to do is plot it and figure out what that velocity profile looks like. And how do we do that? We do that by finding an exact solution to the Navier-Stokes equations. So what we're going to do today in the remaining 10 minutes is to find that equation, the equation of velocity with respect to y that gives me the shape of that velocity profile. So let us begin by writing down the Navier-Stokes equations and seeing where they can lead us. Now we know that Navier-Stokes equations can be written in vector form, just like what I am doing here. However, we also know that based on this description of the flow, there's some simplifications we can make. Based on this description, pressure gradient in this direction, plate moving in this direction, gravitational force acting in this direction, do you think there's any movement, any velocity of the fluid in the z direction? Any? No? Okay. What about in the y direction? Is there any fluid moving, like from here, can move to here?
No, it's just moving in the x direction.
Exactly. We only have movement in the x direction, which means that we really only need the x component of the Navier-Stokes equation. So I'm going to expand the equation in the x direction. The x direction, I have density. I have the material derivative of velocity with respect to time. So just as a review of last week, we had the material derivative, which is equal to the temporal change plus the convective or spatial change. Okay? And then I have my x component of this pressure gradient, which is simply negative tau p tau x. And then I have the Laplacian of the x component of velocity, which is the second derivative of u with respect to x, with respect to y, and with respect to z. And finally, I have my body force. So that is the Navier-Stokes equation for this one-dimensional flow that moves in the x direction. And now let's start to simplify this equation. We know that this plate is moving with a velocity of u. So there is no noted change in the velocity of the plate. It's just a constant velocity. We have a constant pressure gradient. We have a constant acceleration force. Does the velocity change with respect to time? If everything is constant?
No.
No. All my forces are constant. There is no change in velocity with respect to time. Does my velocity change in the x direction? So if I look at a particle here and then I move here, should they have a different velocity or the same velocity? If we're moving along the direction of flow? The same. Okay. Is there any y component of velocity? V? No? Okay. Is there any z component of velocity? No? Okay. I think you can start to see why these equations are very fun to use. I mean, they become very simple. We have a pressure change. We know that. Is there any change in velocity in the x direction? We already agreed that there isn't. Does the velocity change in the y direction? If I look at two different particles along the y direction, okay, so we cannot eliminate it. Does the velocity change in the z direction? No? Okay. And we have our gravitational force. Good. We're getting somewhere. We're getting somewhere. We're getting someplace interesting. Let's look at these pressure terms. Do you think the pressure varies with respect to y and with respect to z, this pressure gradient? Remember, fluid always travels from high pressure to low pressure. So if there is no movement in the y direction, there cannot be a pressure variation in the y direction. Okay? So that means, or would that mean that this pressure cannot vary in the y direction, right? Or do you think it still varies in the y direction? This is x, but I'm talking about y. This is x right now. In the y direction, would that pressure vary? No, right? What about the z direction? No. The reason I'm bringing this up is because even though we have a partial derivative here, because pressure only varies with the x direction, it doesn't vary with y, with z, or with time, then we can express this partial derivative actually as an ordinary or total derivative. Okay, so it's not a partial derivative, it's actually a total derivative because pressure doesn't change with anything else other than x. And now let's look at this rho gx. We know that gravitational acceleration is a vector here, and we're only looking at the x component. So let me perhaps draw this vector here. We have a vector for gravitational acceleration. How do I find the x component of this vector, given the information from the diagram?
Theta.
Sorry?
Using theta.
Using theta, right? How do I use theta? Well, first off, in which direction, right? If my gravity acts in the x direction, should it act this way or this way?
Sorry.
To the right or to the left? Right.
The left.
The left, right? We're looking at the x component of gravity. The x component of gravity acts towards the left, right? I don't want you to be confused. This is not a right triangle, or it's not the right triangle I'm trying to make, okay? How can you then relate your gravitational acceleration vector to the x component using theta? And again, this is not the right triangle I'm trying to make. That's just an unhappy coincidence, okay? How do you think you can relate them? Let me perhaps draw my gravitational acceleration vector here so that it's a little bit better, easier to visualize. My gravitational acceleration acts downwards. We only want the x component of this vector. How do we find it?
G cosine theta.
Close, right? What angle is this?
Oh, no, G sine theta.
That is correct. Remember, we have a 90-degree difference, so it would actually be sine of theta, not cosine theta, because we have this theta angle. We're just moving at 90 degrees. That's all we're doing, okay? So we know, right, that g of x is actually just my gravitational acceleration times sine of theta. But let's take it even further. If I were to look at a right triangle formed by this fluid, I know that for every small change x, I am moving horizontally by some value, and I'm moving vertically by a value that I'm going to call dh. Now, why am I doing this? Because this body force actually gives me the hydrostatic pressure acting on the fluid. And you'll see how in a second, right? And hydrostatic pressure, we know from our original fluids class, our first or second fluids class, was equal to gamma h. This hydrostatic pressure is not the same as this dynamic pressure. Let's keep that in mind. They're different pressures. But here, h is a depth, right? If h is a depth, then h cannot be this y coordinate. H has to be this vertical coordinate. So how do I relate h to x? Through this right triangle. Notice that we have angle theta here. For every x direction dx that you move, you're actually increasing your depth by dh. And so, how can I relate sine theta to x and h? Exactly, right? Sine is opposite over hypotenuse. Therefore, sine of theta is equal to dx over dh. So my gravitational acceleration is actually just gravity times sine of theta, which is opposite over hypotenuse, so dh over dx. And now my body force, rho gx, actually becomes rho times gravity times dh over dx. And what is rho times gravity? Specific weight, right? There we go. So we have an expression for gravitational force. And now let's see what the equation looks like. We have 0, 0, 0, 0. All this becomes 0. The left side entirely becomes 0. On the right side, I have my pressure gradient, my viscous term, and my gravitational term, which is specific weight, dh over dx. Notice that the pressure is actually an ordinary derivative. We already established that it was an ordinary or total derivative. And now we have the operation d dx applied to pressure and applied to gamma h. So we can actually combine these two terms. I'm going to have to rush because we have a minute left. But by combining these two terms, I get d over dx, right? We have pressure. And I'm missing something here, right? What am I missing? In the x direction, right? In the x direction, what am I missing here? Gravity is acting in the negative x direction. Okay? Kind of forgot to do that. So this should actually be negative g sine theta, negative, negative, and negative. Okay? So what I can do is say negative d over dx of pressure. And I'm going to move this gamma. It's a constant. I can do whatever I want with it. I'm going to move it inside the derivative plus gamma h. You can see that we have the dynamic pressure and also the hydrostatic pressure all combined into one beautiful term plus viscosity times the second derivative of velocity with respect to y. Now it's 3:15. If you have to leave, then just leave. I'm going to try to finish this anyway so that I can upload it in the video. But if you have to leave, you can leave and just watch the video so you can see the end of the problem. I won't be offended if you leave. So what do we end up with here? We have a pretty simple equation that relates pressure term to the viscous term. So what does this give me? I get that my viscous term, and I'm just going to keep writing here, mu, second derivative of u with respect to y, equals, and I'm going to move this to the other side, d of pressure plus gamma h over dx. I can then solve for my velocity term, and I get second derivative of u with respect to y equals 1 over mu d of pressure plus gamma h over dx. If the pressure gradient is constant, the velocity is steady, right? It doesn't change with time or with the x direction. We already established that the velocity is steady. So that means that this pressure gradient is constant. Now notice, in the x direction, if I move from here along the x direction to here, would my depth dimension change? Oh, if I move from here along the x direction to here, does the depth from here to here and here to here, does that change?
No.
No. Okay, so that means that this is also a constant. So because it's a constant value, then I can treat all this, and this is just for mathematical simplicity, I can treat all this as a constant. And because it's a constant, just to make our math a little bit simpler, I'm just going to call it lambda, where lambda is some constant. Mu is constant, dp dx is constant, d gamma h dx is also constant. So I can solve this equation, right? I get the second derivative of u with respect to y equals some constant. How do we solve this partial derivative? Or how do we solve this second order differential equation?
You just integrate it.
Integrate. Good. So let's integrate once. We integrate once, and we get that the derivative of u with respect to y equals what? There's a constant. Lambda y, plus a constant, right? I'm going to call it a. Just because you said c, I'm going to say a. And then how do we solve for the velocity field? We integrate again. Exactly. No. I don't want c, I want b this time. So we integrate again, and we get, what's the integral of lambda y?
1/2 lambda y.
Okay, what's the integral of a constant?
Have I redeemed myself from that last time?
Yeah. What's the integral of a constant? Constant times the variable, that's correct. And then what am I missing?
C.
I'm going to call it b. Just so you don't get what you want. Good. So we have a pretty simple equation. And now, is it possible to find these constants? I think it is. Exactly. We need, actually in this case, we need boundary conditions. And I'm going to let you solve this equation by finding these boundary conditions. In tonight's review session, I'll finish this problem. But for now, you have your equation. You find these constants, and then plot your equation, and you'll see what that velocity profile looks like. Okay, thank you for your patience. Sorry that we went a little bit over time today.